Good morning. Today, here we discuss how Earth observation data can be useful in monitoring drought as well as its assessment. There are many approaches has been done over the years which can be useful for the drought monitoring. So, before going into detail about how remote sensing can be used in monitoring drought, we shall understand some basic aspect. As we know, drought is a part of Earth climate and it can occur every part of the world. It cannot recognize regional or political boundary. One more interesting point about the drought is it affects larger number of people in the world. So it is one of the most significant disaster that has been occurring in the last 2 decades. Drought follows plough. That means those areas which are cultivated or more under cultivation are more vulnerable to drought. That is why drought develops slowly, onset slowly and develop cumulatively. By the time we are able to understand that there is a drought, it becomes late for us to recognize with the naked eye. Now here you understand which are the different kind of drought impact on the society as well as agriculture. So drought, first of all, it leads to the drying of the surface and no moisture available for sowing of crops. Another devastating impact may be malnutrition of cattle due to less fodder available for the cattle, and sometimes cattle death also occurs. There is also sometimes problem in the drinking water shortage. There are less availability of the cattle fodder and also migration of people and unemployment. These are the different kind of problem what we see whenever there is a persistent drought occurs in a region. So in India, mainly drought prone areas, they are most of the area confined to the northwest India and some part of the western Ghat area, that is Karnataka. So mainly Gujarat, Rajasthan and also Bundelkhand region and also part of Karnataka region, Karnataka state. They are more or less reeling under drought several times. So which are the area more prone to drought? It is in general arid and semi-arid areas are more prone to drought. And these areas constitute about 68% of the total area. So 33% area which receive less than the 750 mm rainfall and also 35% area which receive rainfall between 750 and 1125 mm. So these both together constitute 68% of area which are more or less highly vulnerable to the drought. If you see the history, then we can see the last decade, 2 decades of the previous century is more under the drought. So frequent occurrence of drought was there in the Gujarat state in particular, but when we see all India figure, then we will find the worst drought was 1987. During 1987, most of the district affected and there was large scale migration of the cattle as well as for famine kind of situation was arise in 1987. After 1987, second worst drought is 2002. Now drought impact already we have discussed, but in total, drought effect may be economical, physical and social, and this effect covers like famine, women suffering, death, abandonment of whole geographical region. So wide intensity drought often claim 50 to 150 million tons of grain. That is the main source of food. So in general, whatever gain we have achieved due to green revolution occur in the late 60s and early 70s is being offset by the persistent drought which hit the India in one or another year. Now you see here one picture that shows people are at hell, not at well. That means such a pretty situation during drought where people has to be in queue for long and long hours for even drinking water. So this is a one kind of example which taken during the 2002 drought. It was one of the severe drought, and this is a picture of Rajasthan. Now drought, we have to understand also drought. In simplistically, drought means imbalance between the supply and demand. Whenever there is a water scarcity, that means physical unavailability of water. So water scarcity with respect to the given demand of a specific region. So whenever there is an imbalance occur between supply of a water through rainfall or other means and demand put forward by the domestic supply requirement, industrial requirement as well as agriculture requirement. So whenever this balance occur, imbalance, then you can say there is a drought. So drought it cannot be defined just like the imbalance between less precipitation and the evaporative demand. It can also cause due to disturbance in the atmospheric circulation, like INSO phenomena, El Nino Southern Oscillation. This kind of phenomena that also bring or lead to the severe drought kind of situation which we have noticed in the early rainy period of current year. In June or July, early July, rain was delayed only mainly because of El Nino heat was there during the current year, and that why in the current year there was a drought noticed in the month of July because of less rainfall received across the India. Now we will see here different kind of drought. There are different kind of drought like meteorological, agricultural drought, hydrological drought, and socio-economic drought. Meteorological drought means degree of dryness. It represents degree of dryness. Whenever there is a rainfall for a particular region in a particular year, received is less than climatologically expected rainfall, then you can say it is a meteorological drought. But agricultural drought has got different meaning. It occurs whenever there is a deficiency of moisture in the root zone to meet the water requirement of crops. That means whenever no adequate moisture available in the root zone to meet the growth and the development requirement of water for the crops, then you can say it is an agricultural drought. Meteorological drought mainly decided based on the meteorological element like temperature, high vapor pressure deficit, less cloud cover, less rainfall, greater sunshine hours. These are the elements which control meteorological drought. But in the case of agricultural drought, one need to take into account the relative availability of moisture in the root zone as well as retention capacity of soil. If clay soil is there, which has got high retention capacity, it can sustain drought. But it can resist drought. But sandy soil, which has got less retention capacity, then it can more or less often subject to the drought because it cannot hold moisture for a longer period or it cannot hold more moisture. That is why area specific, depending upon the kind of soil, moisture variability will be there and which will finally affect the agriculture drought prospect. Third is a hydrological drought. Hydrological drought, it is mainly the drying of surface and subsurface water resources. Whenever rainfall for a longer period decline or less persistent, less rainfall is there, then there will be a drying of lakes, reservoir, pond. And this kind of situation whenever occurs, one can say a region is under a hydrological drought. Then socio-economic drought. Socio-economic drought, that is mainly because of imbalance between the demand for the economic goods exceeds supply. Economic good demand exceeds supply, that means requirement for the tourism, requirement for landscaping, different kind of activity, socio-economic activity which require water. If water is not available to meet this kind of socio-economic activity, then you can say there is a socio-economic drought. Now here you can see a traditional approach for drought monitoring. In this case, mainly rainfall, delay in reduced soil area, delay in lack of rainfall, crop sowing condition. These are the different criteria which are useful for the drought monitoring. This is traditional kind of drought monitoring where rainfall, crop soil area, reservoir levels, these are the different indicators which are used over the period for drought monitoring. But this kind of approach may not be that adequate to represent the large India, having a large biomass with the heterogeneity in the soil and heterogeneity in the topography, heterogeneity in the agriculture crop types. So this information may be useful if it is adequately available from the high resolution satellite data or high resolution high dense network of the rain gauge measurement. Conventionally, India Meteorological Department monitored drought. So conventionally, a region can be classified or a year can be classified as a drought when 75% of its rainfall received in a year is 75% of its long-term average. That means around 25% deficit is there. It can be a moderate drought if rainfall deficit is between 26 and 50. Severe drought if rainfall deficit exceeds 50% of the normal rainfall. So that was the generalized drought characterization based on the only percent rainfall, or you can say percentile rainfall. But over the years, many drought indices have been also developed for monitoring drought. So one of the index popularly used by the India Meteorological Department is aridity index. So India Meteorological Department monitor drought on a weekly basis at sub-divisional scale. So it measures mainly the deviation between the evapotranspiration and the potential evapotranspiration. This index monitoring drought at sub-divisional level. But Palmer drought severity index, which is widely being used by the United States of America, in their digital drought mitigation program. This is an index which is more complex and it is a function of rainfall and evaporation, but it is poor indicator for agricultural drought, or you can say short-term drought, because it is mostly taking into account the weighted function and it can be better useful for the large long-term drought like hydrological drought or some meteorological drought. But in India and other developing countries, standardized precipitation index, which is very easy and simple index, it is entirely based on only rainfall. So India India and other developing countries where measurement network is not dense, or you can say measurement network is very sparse, then it is possible to apply more adequately, more accurately standardized precipitation index to define or depict dry and wet spell at multiple time scale and period. Multiple time scale means 1 month time scale, 2 month, 3 month, 6, 9, 12, 24, 36. So there are different time of month scale can be used. So 1 to 3 month time scale is very much useful for short-term drought monitoring like agricultural drought. 6 to 12 month time scale is useful for the hydrological drought, and 12 to 24 or 48, that may be better indicator for the studying interannual variability in the precipitation. Then also one crop moisture index. It is an index which directly relates to the evapotranspiration and fluctuation in the soil moisture storage. That is why it gains more advantage for capturing agricultural drought, because it is related directly to the crop evapotranspiration as well as soil moisture fluctuation in the soil moisture storage. So CMI gives short-term fluctuation about water status and it is useful for the agricultural drought. This can be calculated within inbuilt function of the farmer drought severity index, but crop moisture index can be calculated on a weekly basis. So this is the approach of drought monitoring by IMD based on aridity index. Here aridity index is calculated based on the soil water balance model. In this soil water balance model, weekly time series of potential evapotranspiration along with the weekly time series of rainfall and the available water capacity. Available water capacity means difference between the field capacity and the permanent wilting point. Based on the individual available water capacity obtained from the soil map of India, that is from National Bureau of Soil Survey and Land Use Planning, time series of PE and rainfall can be used to simulate soil moisture and actual evapotranspiration using the soil water balance model. This actual evapotranspiration along with the potential evapotranspiration then used in computing aridity index. Then aridity anomaly can be calculated by comparing current year weekly time series of aridity index against the previous normal, long-term normal or previous any normal year. You can compute different kind of aridity levels. So this is a different based on the percentile rainfall or severe and moderate drought occurrence, mainly in Gujarat, Rajasthan. These are the area where high frequency of drought occurrence is there. You can see also this high frequency probability of occurrence is more, particularly here, and here also probability of severe drought occurrence is more. Now you can see the episode, particular drought behavior that can be captured with the 3-month SPI in Gujarat. Now here you see different kind of indices are there. One is a 1987, this is 1982, 1998 and 1997. So here you can see, particularly this particular here, it is a 1982 side drought. It is ranging between the -1 to 0. So negative SPI, but only -1 to 0 negative SPI. So it is slight drought. But here you can see this negative. How much negative it is even going -2, 0, -1 and -1, -4.5, 0, 0. So this particular 1987, it is okay. Most of the values are above negative and it is more than -2. So it was the most severe drought. All station was under most severe drought. But again 1988, it is above normal. All SPI is positive, above 0 most of the station. And this is a almost normal year between the 0.5 to -0.5 to +0.5. That is 1997 normal year. So from this you can understand that SPI can be better used for drought monitoring. Now here you can see also in the geospatial form, after geostatistical interpolation of SPI presented for the different month. So you see yellow color, all depicting it is a drought condition. August, September, October, all months were under drought condition. But in 1988, all months were above normal. So it is in blue color. So 1987 was mainly triggered by the El Nino phenomena, and 1988 it was influenced by the La Nina phenomena. So above rainfall, above normal rainfall, below normal rainfall. And it can be categorized based on this US National Mitigation Center classification. It would categorize into different category like this. Okay, so this particular 1987 different drought class, moderate and exceptional drought condition are there. Rest, this is 1982, but 1997 and 88 there was no drought. Similarly, okay, for the district level also you can see the influence of the scale, time scale. If 1 month time scale, which is in 1 month, June month, 1 month SPI, there is no drought for Rajasthan and Gujarat. But once you go to 6 month SPI and 12 month SPI, it is a showing drought. It shows that these Gujarat and Rajasthan, they are inherently dry region, which can be captured by the 6 or 12 month SPI as an indicator of hydrological reside. But 1 month and 3 months, they are the short term drought indicator. So it is as per 1 month SPI and 3 month SPI, these regions were not under drought during the 1988. So this is frequency, district-wise frequency analysis. This is the most highest frequency of drought occurrence in Gujarat, this Bhavnagar, and also district of this Baroda. Another index is crop moisture index. Crop moisture index, which can be evaluated weekly basis. Here you can see particularly the pink dotted line. So initially, during the onset of rainfall was adequate, but there was a occurrence of drought during the mid stage, corresponding to the vegetative phase of most of the crop during July and early August. So this resulted into a drought. So mostly you will find the drought in 2002 is mainly in the mid. This was all about the meteorological drought indices. They are very much useful for monitoring drought if data, particularly rainfall and other meteorological data available in an adequate manner, means partially representative and real time. So, but in India, this rainfall network, or you can say agrometeorological network, is not dense. In India, we have A-class monitoring observatory, hardly 500. But in India, there is large diversity of soil moisture reside because of diversity in the geographical topography, diversity in the soil types, diversity in the land use type, mainly agricultural crops. These diverse land use and topography and the soil types, which result into the diversity in the climate over the different area. So one cannot represent an observatory available, one observatory in one district, that may not be adequate to represent the climate of that particular district. So we need to have a more dense network, then only we can better represent for monitoring drought using this conventional meteorological drought indices. That is why one need to integrate both remote sensing as well as weather information, that means meteorological drought indices, in an integrated manner for preparing regional drought maps. So typically remote sensing is useful based on the interaction of the electromagnetic radiation with the different feature, particularly crop, soil moisture and different parameter. So particularly with respect to agricultural crop, this is the typical reflectance characteristic of vegetation. So how vegetation behaves? In the visible region, because of chlorophyll pigmentation inside the leaves, there is a strong absorption of this wavelength. But suddenly there is a rise in the reflectance in the NIR region because of healthy cell wall interface scattering. So healthy crop, more scattering is there. Then there are three water absorption band. So if high water content is in the leaf, more amount of this, more magnitude of sweep wavelength is being absorbed. Based on this visible, NIR and sphere wavelength, different kind of indices can be generated as an indicator of drought. So satellite remote sensing, how it is useful? It is a main source of the satellite crop related information, particularly because of its large area coverage, multi-frequency, frequent repeat, and data available at the detail what user require. Today we have a satellite kind resolution for drought monitoring ranging from the advanced reefs to almost insect CCD kind of geostationary satellite. So it is a advanced reefs, NOAA, MODIS, OCM, and even geostationary satellite like INSAT CCD are capable of monitoring drought, and these all in the satellite having ability to monitor weekly or fortnightly drought condition over an area. So because of this frequent repeat and the wide range of resolution available to meet the requirement, different kind of indices can be computed from this kind of satellite. One of the commonly used index is a normalized different vegetation index. This is one of the most commonly used across not only India but also in the world. But this particular index has got certain problem. It may not be accurate in monitoring real-time drought because there is an associated time lag response to the drought, or you can say rainfall. Here we try to understand that whenever there is a wetting event, that means rainfall received at the surface, it will penetrate into the soil root zone will recharge. After soil root zone recharge, crop roots will uptake this water and it transfer through xylem to the leaf. Then leaf water status increase. Then leaf from stomata, this water exists to the atmosphere. Then one molecules, similar molecules of carbon dioxide fixed through photosynthesis in the leaves. Then because of the photosynthesis process, new growth, new leaves arise. Once this new resumption of new growth and newly leaves forms, then they can be detected by the remote sensor. So for taking this process, happening this process, it takes almost 2 to 3 weeks to diagnose or to detect drought by the sensor after the wetting event take place. So there is a time lag of 2 or 3 weeks to detect the drought with this kind of normalized difference vegetation index. But another index is there, short wave infrared. Here same thing is there because it is highly sensitive to short term fluctuation in crop water, because it is highly sensitive to the liquid water thickness or leaf water status. So the moment there is a change being noticed in the leaf water status, sensor immediately detect. So it need not to have photosynthesis to occur, new leaves to form and growth to occur, then it is detected by the NDVI. But here, the moment leaf water status increase or change, it is possible to detect by the remote sensor. So it is more sensitive to the real-time drought monitoring or short-term fluctuation. Another is a vegetation condition index. Vegetation condition index, this is also derivative of normalized difference vegetation index, but it is depend on the historical data. Why we need to use historical data? Because drought over the space and time varying. Over the space, there is large degree of variability in sensitivity of different agriculture crops to the drought. You take example of sugarcane, castor, cotton or pulses. Sugarcane or cotton are more sensitive to the drought because they have more water requirement compared to the pulses and castor kind of crop. So, but its effect on the vegetation, normalized different vegetation index, it cannot be used directly to compare drought across different regions with the different kind of crops. So here, using this kind of historical data, we are trying to normalize the geographical difference in the sensitivity of different biomes to the drought. Another index also being developed, that is mainly based on integrating land surface temperature and the vegetation index. So it is more or you can say exploiting NDVI, surface temperature, trapezoid or space. to derive an index which is closely related to the evapotranspiration, water stress and soil moisture. So this is the National Agriculture Drought Monitoring Program, where different kind of data from the in-situ measurement, satellite and models are used for drought monitoring. So weather data, IMD weather observation, rain gauge, geostationary satellite based rainfall as well as automatic rain data, soil moisture, soil water balance model, micro satellite, mainly the satellite like SSMI, our MSMR, SMMR, MSRE. These are the all passive micro satellite which have capability to provide coarse resolution soil moisture on a daily basis. So these kind of coarse resolution soil moisture, they can be better indicator of surface wetness condition. There are thermal data, as we said earlier, that by exploiting NDVI and surface temperature, trapezoid or space, one can also use these kind of indices like TVDI, VTCI to infer soil moisture to certain extent. Crop condition and crop estimation, particularly geospatial near real time from the different satellite. We can get information about the crop status, mainly actual crop status at varying resolution. Biophysical parameter from satellite. From satellite we can estimate LAI, FR, biomass, different kind of variable. Agrometeorological yield model. We can improve agrometeorological yield model also. And improve manual crop estimation survey. Then crop sown area. By having the repeat of daily or you can say weekly, you can enable to monitor the progress of sowing area. Progress of Kharif sown area, you can monitor based on the NDVI if you are having on a daily basis. You can monitor how much area is progressing, or if there is a drought, how much area is being sown. You can give on a weekly basis to the authority. So this is in the case of National Drought Monitoring Program. Mainly it works based on the current year and the previous year NDVI database. So mainly comparison of current year NDVI for particular week against the same week NDVI of normal year. Then the deviation along with the departure time is being used for the depicting changes in the vegetation vigor. So here you can see in for 2002, this brown area, these are under the drought, means very poor vegetation condition it is showing. Then 2002 against the 2001 in June, you can see this red area, that is very low vegetation vigor. That means it is affected by the drought. In case of this Andhra Pradesh, it is done through advanced risk data. Then also this brownish area, that is all showing the agricultural area being affected by the drought or low crop cover condition in 2002. So NAGMAS, this is all about the National Agriculture Drought Assessment and Monitoring System. This is one of the biggest large project in 1989. It is being implemented by the ISRO and it is operationally done earlier through by NRSC. Now a separate center, that is Mahanabolis National Crop Forecast Center, has got a mandate of operationally monitoring agriculture drought. So this Mahanabolis National Crop Forecast Center being institutionalized by the ISRO to have the task of operational drought monitoring. Now, how this in NAGMAS program, how technology has been evolved. You can see in 1988, only NOAA-HR data, which were existing with the frequent repeativity, were used for the monitoring crop conditions. Then once we got our own satellite with the WISP data, 188 meter resolution and the 5 days repeat, we started using IRS WISP data. Then in 2002, WISP data agriculture is being used for agriculture monitoring and supplementation with the MODIS data. Then 2004, we have done more towards the criteria-based decision rule for the drought warning and declaration process being evolved, and all institutional participation and capacity building program also initiated. We have started using IRS advanced risk data with the 1C and 1D. Then further is 2006. You can see 2006 onwards, we are moving towards the more process-oriented modeling and physical algorithm for addressing drought monitoring aspect as well as assessment. So here we are trying to do through from geostationary satellite, evapotranspiration, potential evapotranspiration as an indicator of aridity index. We also use process-based model, mainly energy balance. Residual of energy balance, evapotranspiration is calculated as an indicator of drought. Then this all process-based indicator can go to define different kind of early warning system, vulnerability mapping based on the history of data. Now we have novel chart data with the history. We can say, okay, 15 years of database are there, which can all serve, or even IRS satellite series is also there, which all can serve as a database for identifying vulnerability and risk mapping to the drought. So we are moving more toward the drought risk assessment rather than simply monitoring and preparedness. We are doing drought risk assessment, targeting, prediction, monitoring, assessment, and vulnerability. So nowadays, NDVI anomalies are used, rainfall deviation, soil area also obtained from the remote sensing, soil moisture and evapotranspiration from thermal, geostationary as well microwave satellite data, and also nowadays with the soil water balance model are used for as an input for defining different application of drought. Now drought indices, deviation indices, that is simply normalized difference index of a current particular week or particular month minus NDVI of the normal year, or you can say long term. So this is a formula of NDVI where near infrared minus red divided by near infrared plus red reflectors. This is a one in the image where which you can see deviation index, which can be used for monitoring drought in the Rajasthan. Here you see history, GIMS AHR NDVI of 20 years. Now here you see the lowest. This is a 2002 drought. So here you can see this is it is 1987 followed by 2002. So from here one can say that 1987 was the most worst drought hit, followed by 2002, and this 2003, 2001, these are the all normal year. So this worst drought, this is the normal, above normal and average. In 1987, here you can see NDVI anomaly index. You see all yellow, 2 month. Yellow, this is all drought affected, negative NDVI anomaly. So it is the most drought hit in India. This can be better understand for 2002 drought. Here you can see August, July, August, October, September, all green. There was 2003, there was no much drought, but this yellow patches all, that shows all months were under drought, particularly northwest India and the central India and some part of the Indo-Gangetic plain. And particularly in the Rajasthan, you see 2002, all cropland area were under drought during all 5 months. But 2001, there was no drought. 2003, there was no much drought. But 2000, you can see initial drought was there in the July. And this is very much corroborate with the crop production. 2002, there was drastic reduction in the crop production. And this drought on a seasonal scale, if you integrate over the different months, you can better visualize seasonal scale drought. So this is 2002 seasonal vegetation anomaly, which shows that most of the Rajasthan area were under the drought. But other 2001, 2 or 3, they were not 2 and 1 and there was no much drought affected areas. But in 2000 there were sporadic patches of drought occurrence. And this seasonal vegetation anomaly, it can be better indicator of the drought, and it can be evidence from the strong relationship that exists between the 3-month SPI and the seasonal vegetation anomaly. And it can also give a signal about early assessment of crop loss that occurs due to drought. So there is a strong relationship we found between the food grain anomaly and seasonal vegetation anomaly. So this kind of relationship can be exploited to forecast, or you can say to assess well in advance drought affected losses in the food grains. That VCI, as earlier we have said, VCI formula, it is based on the historical NDVI database, where NDVI mean and NDVI maximum is the absolute mean and maximum NDVI for a particular week in the long-term historical NDVI database. NDVI is the actual NDVI of particular week. Similarly, TCI, that is temperature condition index, and BTmax means brightness temperature. Maximum brightness temperature for particular week in a long-term brightness temperature database. This which can be obtained from the NOAA data. This same type of brightness temperature you can get also from the nowadays Modi's, which has got also history from 2000 to almost 2015. And BT mean is the minimum temperature. Then you can generate a product called vegetation health by multiplying, sharing weightage contribution of VCI and TCI. Here VCI is more sensitive to the soil moisture, and hence it has got more impact on the vegetation growth. But drought effect is not only because of soil moisture, it affects also because of temperature. Like temperature, certain phases of the crops are highly sensitive to the temperature. For example, flowering and podding. Flowering and podding, which is highly sensitive to the temperature, that I am moving to say reproductive growth, which is highly sensitive to the temperature. That is why if you take into account temperature database, it will take care of any stress during the flowering or reproductive phase due to drought. VCI, this is generated for deforestation sites Alwar, Jaipur and Jaisalmer. So here you can see 20 or less than 35% VCI, that means a severe drought, and if it is a VCI is equal to 50% reflect fair vegetation, VCI 0 means dry month. Here you can see this is a vegetation health product for 2002 compared with the 2001 for the every daily basis, July 21 and August 04. Here you see 2002 all red orange area, that shows drought affected areas. Vegetation cover, vegetation stress was there. But here same area in 2001 was not under the drought. Another index we have tried to develop by integrating remote sensing based indices, that is mainly vegetation condition index, with the rainfall. So here we have tried to develop newer indices called vegetation drought index, combining vegetation condition index and rainfall anomaly index derived from the CPC rainfall, that is Climate Prediction Center rainfall, which is available on the 10 kilometer grid. So first we have computed modified rainfall index by taking into account weightage of previous 3 decades contribution to the drought. Then that MRI and the VCI has been weighted with the equal half contribution to get the vegetation drought index. So here you can see this is vegetation drought index, which shows that these are the drought areas. And here in 2003 you see same vegetation index. It shows 2003 was normal year and there was no only moderate marginal drought, only some sporadic patches. Otherwise, most of the Bundelkhand region was under normal condition during 2003. Another indicator, as we have discussed earlier, vegetation temperature condition index, which can be derived by taking into account the NDVI surface temperature trapezoid. So by exploiting this space, we can compute vegetation temperature condition index, which ranges from the 0 to 1. 0 means dry condition, water limited. 1 means adequate vegetation or no drought. Higher the occurrence, higher the value of VTCI, higher the lower value of VTCI, higher the occurrence of drought. It can be parameterized based on the trapezoid like this. This is upper line which reflect the minimum evapotranspiration line. This is a maximum evapotranspiration line which can be derived based on the fitting the regression to the LST minimum values for defined sorted NDVI interval, and this is LST maximum value for the individual every NDVI interval sorted out. So from these two regression we can get LST max and LST min, and then we can compute VTCI. So this is the one which we have done for the 5 years for the Gujarat region, defined this VTCI, and it has been used as an indicator of stress condition. So here you can see 2004 there was no stress, 2001 there was stress was there, 2002 and 2000. Now we see that drought duration can also be computed directly from this kind of weekly base or 8 days VTCI. So this is 2002. Number of period, 8-day period were more under the drought compared to the 2003 and 2001 and 2000. So this is same, these advanced partial vegetation indices as we have earlier shown, VCI and MRI. Another, one can also integrate soil water balance modeling, particular crop specific water balance model with the remote sensing, derived length of growing period, also rainfall, rain-based network with the geostatistical interpolation technique to derive the rainfall and available water capacity. This information can help you to drive crop specific water balance model and finally compute water requirement satisfaction index, which is a function of rainfall, potential evapotranspiration, available water capacity, crop types, start of season, length of growing period. Here we try to assess length of growing period for the 7 years, and here you can see particularly 2002, very less. You can see very less period. Means it was 2002 and 2003. So 2002, it is mainly 90 to 100 days crop growing period were there, but in 2003 very high. So in 2002, length of growing period was reduced almost by 20 to 30 days due to drought, and this finally affected the water requirement satisfaction index. So here you can see the for sorghum, per millet and maize, we have computed the water requirement satisfaction index for the 2002 and the 1998. So here you can see this is drought, WRS, bad crop, and this is a good crop. So this was a non-drought year, and here you can see 2002 crop condition water requirement satisfaction index is very poor, and it is a bad crop affected areas. Globally, people use different kind of scenario, different kind of drought indicator, and finally drought assessment. For in US, there are farmer drought indices, CPC soil moisture model, stream flows, standardized precipitation index, and satellite derived vegetation health product. These 5 indicators integrated to derive final drought maps. So US even going further, they are trying to develop a newer index, or develop index for monitoring. There is vegetation drought response index, which integrate satellite derived parameter, climatic component like standardized precipitation index, farmer drought severity index, and also biophysical environment like land use, soil types, ecological condition to derive final drought condition map. So nowadays, with the availability of history of the rainfall database like CRU database, Colorado Research Unit database available for almost you can say 100 years. These all database that can pave way for computing indices, newer and newer indices like standardized precipitation index, standardized precipitation evapotranspiration index for studying interannual variability in drought. So different time scale SPEI has been computed over the whole globe as an indicator of drought. Now it is gaining wide popularity because it takes into account both rainfall as well as evapotranspiration. Standardized precipitation index, it takes only the rainfall. But now this is a better indicator because it takes into account both rainfall and the precipitation to construct the index for the drought. And it is multi-scalar also. So if we have to have evolved some newer national drought information early warning system, it should have certain kind of component. What I opine that understanding of regional drought characteristics we should have. We should understand first of all what are the agroclimatic vulnerability to the drought across different regions, and moreover, if possible, crop specific drought vulnerability need to be analyzed well in advance to address drought aspect. Then prediction of long-term drought based on some statistical modeling, or you can say ISO-based indicator. Then monitoring of short drought can also be possible through integrating weather forecast or seasonal weather forecast with the crop model and the remote sensing. One can enable to make short-term forecast and drought alert and irrigation advisory service if this kind of weather drought forecast about the soil moisture, about the water availability, irrigation requirement can be analyzed together with the irrigation advisory and the soil moisture model. One can form irrigation advisories also. So this is a long term, okay, so drought linkage can be developed, calculation of interannual change, generation of long term meteorological data like. So there is one. In India mainly, if you see the rainfall, all India summer rainfall situation, now there is a strong relation happening between the INSO and the rainfall. So if you see La Nino, blue is a La Nino, red is a INSO, and this is a drought, bar is a drought. So whenever there is INSO condition, that means El Nino, southern El Nino phenomena is there, then there is a drought. It is because INSO El Nino is directly related to the dry event, and La Nina is directly related to the wet event. So whenever El Nino is there is a more probability of drought occurrence in India. So this is what we have also analyzed: 1988 La Nino, 1987 El Nino, and we got also with the Southern Oscillation Index good correlation between the rainfall anomaly as well as food gain anomaly. So 3-month PSTI is a good indicator of drought, and there is also this INSO index can be an indicator of regional drought. Soil moisture nowadays, okay, this is the soil moisture assessment which has been done based on the soil moisture model, soil water balance model, on operationally being analyzed by under the National Agriculture Drought Assessment and Monitoring Program and given available on Bhuvan also. So similarly, agriculture drought assessment for current September 2014, it is categorized into the area which is normal, mild drought and moderate drought. So moderate drought area in this September current year, it was this Rajasthan and some area of the Tamil Nadu and some part of the this Maharashtra, or you can say some Andhra, Maharashtra. Okay, some one or two districts in Gujarat. So these are the area which were affected by the drought in the current year. So this is the approach what you can implement if you want to have prediction of the short-term drought, crop-specific drought. So you can integrate regional climate model, crop model like DSAT or WAPOST or InfoCrop, regional climate forecast like RACM or WRF forecast, and remote sensing data you can use for the adjusting this drought stress index which you can simulate based on the modeling, and then finally we can have a drought forecast. So this is one, okay, what we have seen based on the climate forecast, seasonal climate forecast used to compute the SPI, Standardized Precipitation Index. Here you can see 3-month SPI of September. So particularly July, these are where the area in the current year were under the drought, and then okay it is moving, okay, August, these were under drought, and this September, these area were under the drought in the current year. So these were data where these are the different kind of maps which we forecasted in the May itself using the regional climate seasonal forecast, ECOM downscale with the RACM and computed SPI. Thank you.